When you're really trying to, get down to the nitty-gritty, like the very foundations of things, it's easy to get lost.
Oh, yeah. Especially in philosophy, right?
Yeah.
You want that core, that bedrock understanding.
Exactly. And you don't want to drown in a sea of complexity.
Right. You want those aha moments, those flashes of insight.
So today, we're going deep, but we're going for clarity. We're diving into alternative axiomatic set theories. It's like exploring different blueprints for the whole mathematical universe.
Think of it as a deep dive, right into the foundations.
Mm.
And while a lot of folks in math might think ZFC, that's Zermelo-Frankel set theory, with the axiom of choice is like the end-all be-all.
The gold standard.
Yeah, exactly. But for us, thinking philosophically,
Yeah.
it's super important to remember that ZFC is not the only game in town.
Not even close.
The sources we've got lined up today, they show us there's this whole rich landscape of other ways to think about sets.
A whole buffet of set theories.
And each one gives us like a unique perspective on some really big questions. Infinity, truth, even existence. Heady stuff.
Exactly. This deep dive is your express lane to understanding these different foundational ideas.
We're not just taking ZFC for granted.
Nope. We're going to tinker with the rules, see what happens, shake things up a bit.
And as our sources point out, getting a grip on these alternatives, it's like shining a light on what any set theory, even ZFC, is really trying to do.
It's like seeing a building from all different angles. You really understand the design choices.
Exactly. You see why things are the way they are. And for philosophy, this is not just some abstract side trip, right?
No way.
Set theory, it gives us the very language, the framework for all these foundational debates. In math, in logic, even metaphysics, it's where we grapple with infinity, where we try to build like the most basic math ideas from even simpler concepts.
Like, think about the real numbers. You know, that continuous line we all learned about.
Yeah. Dedekind showed us how to build them from sets of rational numbers. It's a powerful demonstration of set theory's foundational reach.
It's mind-blowing. And the natural numbers, 0, 1, 2, and so on.
Frege and Russell took it even further.
Yep.
Right? They defined those as sets themselves.
Whoa, wait. What does that even mean?
So, like the number 3. In their view, it becomes the set of all sets that have exactly 3 elements. It's like, whoa!
It's getting deep.
It really shows you the power we're talking about here, this foundational power of set theory. But this journey to solid foundations, it wasn't always smooth sailing.
Uh-oh, what happened?
Early on, naive set theory, which relied more on intuition than strict rules, encountered some big problems, like contradictions.
Paradoxes.
Right.
The infamous paradoxes of set theory.
Exactly. And the one that really shook things up, that was Russell's paradox.
Oh, yeah. That one's a classic. Elegant, but brutal.
Right. It's so simple, yet so devastating. Think about the set of all sets that don't contain themselves.
Okay, I'm thinking about it. Sounds harmless enough so far.
Now ask yourself, does this set contain itself?
Well, if it does, then by definition it shouldn't. But if it doesn't, then it should. It's like a snake eating its own tail.
It's a self-contradiction. It exposed a flaw, like a crack in the foundation, in the idea that any property could define a set. No restrictions.
So that's where things went wrong.
Right. These paradoxes, especially Russell's, they were a wake-up call. They pushed mathematicians and philosophers to develop like more rigorous systems.
Yeah.
They needed to define the rules of the set theory game much more carefully.
And that's where our journey into these alternatives really begins.
Yeah. Different thinkers trying to navigate those tricky logical waters.
Okay, so let's unpack the first response, these typed theories.
Right. So the simplest one, they often call it TST. It brings in this idea of different types of objects, organized in a hierarchy, kind of like levels.
A hierarchy.
Yeah, indexed by the natural numbers, like levels of existence for sets.
Okay, so it's all about categorization to prevent those paradoxical mix-ups, right?
Exactly, like type 0. That's your ground floor, the fundamental building blocks, maybe things that don't even have any set structure themselves.
Okay, I see.
Then type 1. It has sets whose members are all from type 0, type 2, sets of type 1 sets, and so on. You climb the ladder.
So it's like a ladder of sets.
Yeah, and the key thing is a very language of TST enforces these distinctions. You can only talk about equality between things of the same type.
Apples and apples, not apples and oranges.
Exactly. And something of type N can only be a member of a set of type N plus 1. It's like making sure that when you describe a relationship, the things you're talking about are on the right levels of abstraction.
So it's all about keeping things organized. How does this actually avoid the paradoxes, though? Like Russell's paradox.
Ah, good questions. So that set of all sets that don't contain themselves.
The one that broke naive set theory.
Right. In TST, that concept becomes like grammatically incorrect. It's like saying cat, dog, run.
Hmm.
It just doesn't make sense in the language.
I see.
For a set to contain itself, it'd have to be, say, type n, but also be a member of something of type n plus 1, which is itself.
Mhm.
But the rules only let you have members from a lower type.
So the self-reference is blocked at the language level. Very clever.
Right. That self-referential set, the
Yeah.
heart of the paradox, you can't even write it down in TST. It's like the paradox is dissolved before it can even start.
That's pretty elegant.
It is. And the axioms of extensionality and comprehension in TST, they look a lot like those in naive set theory,
Yep.
just with these extra type constraints.
So they keep the basic idea of sets, but with safety rails.
Yeah, it's like an attempt to hold on to that intuitive appeal of set theory, but avoid the pitfalls, the logical traps.
I can dig it.
But wait, there's more. Some typed theories, like Russell's original system and something called predicative TST, they get even stricter.
How so?
They introduce this idea of predicativity. Basically, you can't define a set by referring to a collection that includes the set you're trying to define. No circular definitions.
That's reasonable.
It is, in a way. It's another way to block that kind of circularity that leads to paradoxes.
Yeah.
But it also limits what you can do.
Ah, so there are trade-offs.
Always. Like defining the natural numbers in the usual way becomes tricky because it kind of looks like you're quantifying over all sets of natural numbers, including the one you're building.
Oh, right, because you're saying, like, the set of all sets that follow these rules, but those rules include the set itself. That's circular.
Exactly. And the least upper bound axiom. Yeah. Super important for real analysis, but it runs into trouble in these predicative systems. Russell even tried to fix this with something called the axiom of reducibility, but even he wasn't totally happy with it later on.
So it's like a balancing act, right? You want to avoid paradoxes, but also want a system strong enough to do real math.
Exactly. It shows that inherent tension, between wanting a safe system and a powerful one.
Right. And it's interesting how type theories, even though strict predicativity isn't super popular in math these days, they still show up in places like computer science for designing programming languages, right?
Absolutely. It's about making sure the systems are robust,
Mhm.
that they won't crash because of some unforeseen logical loop.
So typed theories are one path. What was the next big step in formalizing set theory after those paradoxes hit?
Our sources point to Zermelo's set theory, right?
Right. Zermelo, 1908, a big moment. It was like, okay, let's get serious about this. We need a better system, one that's rigorous and can handle the paradoxes.
He laid down the law with a specific set of axioms, like rules for what sets exist, no questions asked.
And what were some of those foundational axioms?
Well, you've got extensionality, still the same idea from before. Two sets are identical if they've got the same elements.
Right, the two sides of the same coin idea.
Exactly. And then there's pairing. For any two objects, boom, there's a set containing just them. Union, that's for sets of sets. You get a new set with all the elements combined. Power set, for any set, there's another set containing all its subsets. And then infinity, which guarantees that at least one infinite set exists.
So this is starting to sound familiar, like those early set theory ideas, but with more rigor.
Precisely. It's like taking those intuitive ideas and making them precise.
So what about separation? That seems to be a big one for dealing with Russell's paradox. How does it work?
Separation is key. It says if you have a set, let's call it A, and a property, we'll call it Px, that you can define with a formula, then you can create a new set with all the elements of A that have that property.
So it's like filtering a set based on some criteria.
Exactly. But here's the crucial part. You're always making a subset of an existing set. That's the big difference from naive set theory. There, you could just define a set based on any property leading to those paradoxes.
So you can't just conjure sets out of thin air based on any crazy idea you have.
Right. It's more controlled. Like with Russell's set, you'd be saying, give me all the elements of A that don't contain themselves. But now, you're restricted to A. You're not talking about all sets in the universe, just those within A.
So it's a much more limited and safer kind of comprehension.
Right. It avoids that self-referential loop that was causing trouble. You don't get that contradiction. And it also tackles the idea of a universal set, the set of all sets.
Ah, right. That seems like it would be a paradox waiting to happen.
Exactly. Zermelo's system shows that such a set can't exist. If it did, boom, you could just use separation to make the Russell set as a subset, and you're back in trouble.
So no set can contain absolutely everything. It's like those absolutely infinite collections Cantor talked about. They're just too big to be sets.
Right. Zermelo's system aligns with that idea. And, it's interesting that almost all of Zermelo's axioms had some kind of informal counterpart in naive set theory.
So it was about cleaning up and formalizing those intuitive ideas,
Yeah.
making them precise and paradox-proof.
Exactly. And then we move on to ZFC, the standard set theory we use today.
So how did we get from Z to ZFC?
Well, over time, they refined Zermelo's system. Most importantly, they added the axiom of choice
Right.
explicitly.
Oh, yeah, the axiom of choice. That's a whole other can of worms.
It is. But they also made the axiom of separation super precise, referring to first-order formulas.
Okay.
And they ditched the idea of atoms, those things that aren't sets. ZFC focuses purely on a universe of sets.
So it's a pure set theory, no atoms allowed.
Exactly. And two big new axioms came into play: replacement and foundation.
Okay, choice is controversial, we know that. But what about replacement and foundation?
Replacement is a powerhouse. Imagine you have a set A and a relation that acts like a function on A's elements. For each element in A, you have a unique output.
Like a mapping from one set to another?
Yeah, precisely. Replacement says the collection of all those outputs is also a set. So you can build much bigger sets than you could with just Zermelo's original axioms.
So it's an axiom for creating big sets. What about foundation?
Foundation is all about structure. It says that every non-empty set has an element that's totally separate from it, no shared members.
So no sets that contain themselves or infinite loops of sets within sets?
Exactly. No infinite descending chains either, like no set by 1 that contains by 2, which contains by 3, and so on forever.
It's all about making sure the sets are built up from simpler things, right? Like a tower, not a tangled mess.
Right. And this well-foundedness is closely tied to the idea of the cumulative hierarchy of sets. It's like building sets in layers from the ground up.
So Zermelo's theory couldn't really prove all those layers existed, but ZFC with foundation really nails it down.
Right. And just to add a little extra, there are weaker versions of ZFC, like McLean set theory. It's actually equivalent to TST with infinity, which is kind of cool.
Showing that even within a certain approach to set theory, there are still choices to make, different levels of strength.
Exactly. And then there's Kripke-Platek set theory, important in model theory. It focuses on absolute constructions, things that stay the same across different models of set theory.
So it's like zooming in on specific types of constructions.
Right. And it actually drops the power set axiom altogether.
Wow, no power set. That's a big difference.
Yeah.
So we've got type theories, Zermelo's system and its refinements, and now, what about those theories that go beyond sets, the ones that deal with classes?
Ah, yes, the theories with classes. So why bring classes into the picture?
Well, from what I understand, it's because sometimes you want to talk about collections that are just too big to be sets in ZFC, like all sets or all ordinals. If those were sets in ZFC, we'd be back to those paradoxes.
Exactly. So you need a bigger bucket, and that's where classes come in.
A bucket for big ideas.
Right. You've got proper classes, which are these giant collections that can't be members of anything else. That way you can talk about those massive concepts without breaking the system.
So classes are like the supersets of set theory.
In a way, yeah. And one of the best-known theories with classes is von Neumann-Gödel-Bernays set theory, or NGB.
Okay, so NGB is all about sets and classes. How does it tell them apart?
Well, in NGB, sets could be members of other classes, but proper classes, they stand alone. They're too big to be elements of anything.
Makes sense. So how does NGB avoid those paradoxes with these classes running around?
NGB has clever axioms. You can make a class from any property, but only if the formula defining it talks about sets. You're not allowed to quantify over classes.
So you can't say, like, the class of all classes that don't contain themselves.
Precisely. That would be trouble. And because of this, the Russell class, the one that gave us so much trouble, it has to be a proper class in NGB.
So it exists, but it's kept safely out of reach of the paradoxes.
Exactly. And NGB often has this really neat axiom, the axiom of limitation of size.
Okay, what's that one about?
It says that a class is a proper class if and only if you can match it up one-to-one with the entire universe of sets.
So it's about comparing the size of classes to the universe of sets.
Right. And this axiom, as simple as it sounds, it has huge implications. It actually implies both replacement and choice.
Whoa, that's powerful. So you get those key axioms from a very different starting point.
Exactly. It shows you how these foundational ideas can be interconnected in surprising ways.
And what about Kelly-Morse set theory? I know our sources mention it as being even stronger than NGB.
Yeah, Kelly-Morse, it takes things up a notch. It says, hey, let's be bold and allow quantification over all classes, not just sets, when we're defining classes.
So it throws open the doors to talking about classes in a much more unrestricted way.
Exactly. And because of this, Kelly-Morse is seriously strong. It can actually prove that ZFC is consistent, something ZFC itself can't do. Gödel's incompleteness theorem, remember?
Right, so it's like standing on higher ground, able to look down and say, yep, ZFC is doing okay down there.
Precisely. It gives you a different perspective, a meta-perspective on the consistency of ZFC.
Fascinating. And then we have Ackermann's set theory. That one seems particularly interesting because our sources describe it as being a genuine alternative to ZF, but also basically equivalent in a lot of ways.
Ackermann's set theory is a fascinating beast. It takes a totally different approach, but ends up in a surprisingly similar place. It's a universe of sets and classes, but being a set is not just about being a member of some class. It's a fundamental property defined by its own axioms.
So it's like sethood is a built-in feature,
Yeah.
not derived from membership.
Exactly. And it's got axioms like anything in a set is itself a set, and any subset of a set is a set. Pretty intuitive, right?
Yeah, those make sense.
But the crazy thing is, despite these different starting points, Ackermann's theory can prove infinity. And if you just look at well-founded sets, those without infinite descending chains of membership, it's essentially the same as ZF.
Whoa, that's wild. So you can get to the same place via two very different routes.
Exactly. And to show this equivalence, they often use the reflection principle of ZF. It basically says, any true statement about the whole universe of sets is already true in some big enough initial chunk of that universe.
So it's like a fractal pattern where the same structures repeat at different scales.
Yeah, kind of like that. And another interesting point is, unlike NGB, Ackermann's theory allows classes to have other non-set classes as members.
So it allows for a slightly weirder hierarchy of collections.
Right. It's a subtle difference, but it shows that even when two theories seem to agree on a lot, they can still have these interesting points of divergence.
Okay, so we've seen type theories, the Zermelo line, theories with classes, and now onto something completely different, Quine's new foundations.
NF, yes. A bold attempt to create an untyped set theory.
Right, untyped. But didn't we just spend all this time talking about how types help avoid paradoxes?
Exactly. It's like, okay, let's throw out the rule book.
Yeah.
Quine, he was looking at type theories and noticed something interesting. When you take a formula and bump up the type of every variable by 1, you get a formula that acts almost the same logically.
So it's like shifting everything up a level, but the logic stays similar.
Right. And this made him wonder, maybe those types are kind of artificial. Maybe we can do without them.
But how do you avoid those paradoxes without the safety net of types, especially Russell's paradox?
NF has this clever restriction on its comprehension axiom. It's called stratified comprehension. It says you can only create a set based on a formula if that formula is stratified.
Stratified, what does that mean?
Think about assigning a number, a type index, to each variable in the formula.
Okay, I'm following.
Now, whenever you have x belongs to y, the number for y has to be exactly 1 more than the number for x. And if you have x equals y, they get the same number.
So it's like those type rules we saw before, but applied to the formula itself, not to the sets directly.
Precisely. It's about the syntax, the way the formula is written.
Yeah.
And guess what? The formula for Russell's paradox, x, doesn't belong to x. It's not stratified.
Uh-huh. So you can't even form that paradoxical set because the formula itself is illegal.
Exactly. It's blocked at the language level.
Yeah.
And here's the kicker. NF does have a universal set.
No way. The set of all sets, that's not allowed in ZFC.
Right. But in NF, the formula x equals x is stratified. So you get this universal set, and get this, it's a member of itself.
It contains everything, even itself. Mind-blowing.
I know, right? And a lot of standard math can be done in NF,
Uh-huh.
but it has some quirks. For one, the axiom of choice,
Mm.
it doesn't work in NF. Stucker proved that.
Wait, no choice. That's a pretty big difference.
It is. It means that in NF, you can't well order the whole universe of sets.
Oh, so you can't line up all the sets in a nice ordered sequence.
Exactly. But here's another weird thing.
Yeah.
In NF, you can actually prove that an infinite set exists. You don't need an axiom for it.
So, a set theory where choice fails, but infinity is a theorem. That's a very different universe from ZFC.
It is. And our sources mention NFU, new foundations with your elements. It's a tweak to NF.
Elements.
They're like atoms, things that aren't sets.
Uh-huh.
NFU loosens the rules a bit to allow for these your elements.
So it's like adding a new fundamental building block to the mix.
Exactly. And this change has a big impact. NFU is actually consistent with both infinity and choice, and even with denying infinity.
So you can have an NFU universe with or without infinity?
Yep. It's weaker in terms of consistency strength than Peano arithmetic. which is the standard way to describe the natural numbers.
That's crazy. So by adding these elements, you get a completely different set of possibilities.
Right. And there are even weaker, more restricted versions of NF, like NF3 and NFSI, where they limit comprehension even further. It's a whole family of set theories with different strengths and properties.
And the fact that we can create models of NFU within standard set theory, it's like finding a secret passage between these seemingly different worlds, like they're more connected than we thought.
Exactly. And the math in NFU is interesting, too. It has its own way of avoiding those paradoxes, often due to how the singleton map and operations on ordinals behave. It challenges those ideas from Cantor and Brawley-Forty in its own unique way.
So even though it's different, it's still a rich and valid mathematical system.
Absolutely. NFU, especially with infinity and choice added, it's a real contender, a genuine alternative to ZFC. And it shows that math isn't just about one set of rules. There are options.
Okay, so we've got type series, Zermelo's system and its variations, theories with classes, and this whole Quine-inspired universe. But what about those positive set theories? What's the deal with those?
Positive set theory. It's like looking at set theory through rose-colored glasses.
Positive vibes only.
Kind of, yeah.
Yeah.
The main idea is to build the foundation using only positive formulas. No negation allowed.
Wait, no negation. That sounds like a huge limitation.
It is a big change. You're restricted to things like conjunction, disjunction, and quantifiers. But no, not. You can't say, this set doesn't contain that.
So why do that? What's the point of giving up such a basic logical tool?
Well, there are a couple of reasons. Firstly, paradoxes like Russell's, they rely on negation. If you can't say not, you can't even formulate the problem.
I see. No negation, no paradox.
Clever. Right. It's a way to build a system that's inherently free from those contradictions. And secondly, there's this connection to topology, which is a fascinating branch of math.
Topology, like the study of shapes and surfaces.
Exactly. If you think of sets as being like closed sets in a topological space, then certain operations on sets, like unions and intersections, they correspond to operations in topology.
So it's like a different way of visualizing what sets are and how they behave.
Precisely. It gives you a different mental picture. And because of that, positive set theory often has a very different feel to it.
Okay, so we've got this negation-free world. Our sources mention a specific system called GVK plus infinity, developed by Olivier Esser. What's special about that one?
GPK plus infinity, it's got a few key axioms. You have the usual extensionality and then a generalized positive comprehension principle. It's like regular comprehension, but you're allowed to use bounded quantifiers in those positive formulas.
So it's slightly more expressive than just basic positive formulas.
Right. And then there's a closure axiom, which says that for any class, you can find a set that's its closure, kind of like a minimal container for it.
Yeah.
And it also has an axiom of infinity, but it's formulated in a way that avoids those self-reference problems.
So even infinity has to be handled carefully in this system.
Exactly. But here's a really cool part. GPK plus infinity is surprisingly strong. It can actually interpret both ZF and Kelly-Morse set theory.
Wow, so this system with no negation can somehow encompass those other seemingly more powerful systems.
Yep. And it can even prove results about large cardinals, which are these massive sets that go way beyond the usual infinities.
So it's not just consistent, it's powerful too.
Exactly. But there's a catch.
Mm-hmm.
The full axiom of choice, it doesn't work in GPK plus infinity. It's too strong, it clashes with the positive nature of the system.
So again, a trade-off. You get power and consistency, but you lose the full strength of choice.
Right. But you can still have choice for well-founded sets, which is interesting. It's like, choice is okay as long as you stay within the well-behaved part of the universe.
Fascinating. So positive set theory, it's a radical departure from the usual way of doing things, but it's still capable of amazing things.
And now we delve into the world of set theories inspired by specific logical or philosophical views.
Set theory tailored to particular worldviews.
Exactly. And one of the most prominent examples is constructive set theory.
Constructive set theory, I've heard that term before. It's connected to intuitionistic logic, right? Where you need concrete evidence for everything.
Exactly. No fuzzy, non-constructive proofs allowed. Intuitionism is all about building things up step by step. So constructor set theories, like intuitionistic new foundations, INF, intuitionistic ZF, IZF, and constructive ZF, CZF, they take the standard set theory axioms and give them a constructive makeover.
So you can't just wave your hands and say, oh, this set must exist because it would be weird if it didn't.
Nope. Everything needs a recipe, a construction. And that means some things that are taken for granted in classical logic, like the law of excluded middle, where a statement or its negation must be true. They don't fly in intuitionism.
So it's a much more restricted logical environment. Does that make constructive set theory weaker?
It's different, not necessarily weaker. It just asks different questions and has different standards of proof. Some things that are classically equivalent might not be in constructive set theory.
So like parallel universes of logic and mathematics.
Exactly. And axioms have to be chosen very carefully so that they have constructively valid interpretations. Even the axiom of foundation, the one about no infinite descending chains, it can be problematic because some versions imply the law of excluded middle.
So even foundational principles need to be re-examined from this constructive perspective.
Precisely. And the power set axiom, that one's viewed with suspicion too, because it's not really constructive. You're just asserting that the set of all subsets exists, but can you really construct it?
Right. It's like saying, here's a bag that contains all possible bags. How would you even make that?
Exactly. That's why systems like CZF often leave out the power set axiom altogether. They're more cautious about what sets they allow. And ultimately, these constructive systems, they change how we think about mathematical objects, proofs, even existence itself.
It's a very different way of doing math, grounded in a different philosophy of what math is.
Precisely. Now, what about set theory for non-standard analysis?
Non-standard analysis, that sounds intriguing. What's the connection to philosophy and logic there?
Non-standard analysis is all about giving a rigorous foundation to those intuitive ideas of infinitesimals and infinite numbers.
Mhm.
The things they used in early calculus, but in a less formal way.
So it's about making those informal ideas precise and rigorous.
Exactly. And Nelson's internal set theory, or IST, it does this by saying, hey, let's add a new concept to set theory. Standardness.
Standardness.
You have this new predicate SX, which means X is a standard set. It's like a label you can put on sets.
Okay, so some sets are standard and others aren't.
Right. And IST takes the usual ZFC axioms, but with a twist.
Yeah.
You can't use SX in the formulas for separation and replacement. It's like standardness is a fundamental property. It doesn't depend on how you define sets.
I see. So it's like layering this idea of standardness on top of the usual set theory.
Exactly. And then IST adds 3 new axioms to deal with standard and non-standard sets. There's idealization, which says that if every finite part of a set has a property, then the whole set, in a way, almost has that property with respect to standard elements. It's a bit technical, but it helps capture those ideas of infinitesimals and infinite numbers.